Hello, classmates. Hello, professor. Today we're going to talk about an article titled "The First Derivative Spectrophotometric Determination of Copper and Nickel Simultaneously Using 1,2-Hydroxyphenylthiourea." The analytical problem that the professor gave us was the determination of copper 2 in aqueous solutions. And in this paper, we found that they did that, but they did it along with the determination of nickel 2, but it accomplishes and answers the problem that was initially given by the professor. Basically, what they did here is that they did a complex between nickel and the 1,2-hydroxyphenylthiourea, which is going to be referred to as HPTU. It's kind of easier, right? And also they did the same with the copper. So and those complexes were the ones that were determined, and then uh, then they could determine the actual copper and nickel contents. Basically, after they synthesized the HBTU, they made it into a coordination compound with the metals, and after that they used first derivative spectrophotometric determination. My partner is going to later explain what does that mean. Mm, And after that, what they used for getting a little bit faster, a little bit to use a little bit less time in the reactions that took place, were some surfactants. So surfactants are just tensioactive agents. And what they do is they break the surface tension of the solvent, which in this case would be water, since we're talking about aqueous solutions. And what they will do is they will act kind of like a soap. They will make some micelles in the water. And as you can remember, a micelle is a little like a sphere with hydrophobic end towards the center of a sphere and the hydrophilic end towards the outside, which is where is going to be the solvent, right? So the micelle as a sphere has a very big surface area, and as you might remember from the chemistry 2 course and some kinetics in chemistry, the largest the surface area is, well, the fastest the reaction will go. So this is kind of like a catalyzer. It's not actually a catalyzer, so as here it says, is used as an activator. So activators will do this, will kind of catalyze, but they are not actually catalysts. So these substances that were used were the cetyl methyl ammonium bromide, which is CTAB, and the sodium dodecyl sulfate, which is going to be referred as SDS. Now my partner is going to continue.
Spectral differences. uh, they are produced when the absorption of an interference species overlaps or appears to approximate to absorptions of analyte, which results in an impossible resolution by the monochromator. These interferences exist also due to combustion products, which have broad absorption bands or are in the form of particles which scatter the radiation. Both of them lead to positive errors by diminishing the light beams. Chemical interferences. They are more common than spectral ones. They occur when sample reacts with other chemical species, affecting the absorptions. Their effects can be minimized by choosing the aqueous environment. Nowadays, there is evidence of process carried out in the flame that they approximate to the thermodynamic equilibriums. um, the dissolutions, ionizations, and slightly volatile. Bros formations equilibriums are the most interesting.
Okay, so the method used was the first derivative spectrophotometric method. And well, in the screen we see basically you can read how it was done in the laboratory by them, by the creators of the article. But we are going to go a little bit more deeper into the theory of what this method is actually, because they just mention it that they use that, but they don't actually give us a theory on how that works. So we're going to go a little bit more deep into that. So if you can continue.
First derivate spectrophotometry. Derivate spectroscopy uses pairs or higher, higher derivatives of absorbance with respect to wavelength to, for qualitative analysis and for quantifications. Figure 1 shows a computer simulation of the effects of derivations on to appearance of a simple Gaussian absorbance band. Derivative spectra are always more complex than zero-order spectra. A first-order derivative is the rate of change of absorbance with respect to wavelength. Um, to wavelength. A first-order derivative starts and finishes at zero. It also passes through zero at the same wavelength as the maximum absorption wavelength of the absorbance band. Either side of this point are positive and negative bands with maximum and minimum at the same wavelength as the inflection points in the absorbance band. This bipolar function is characteristic of all odd-order derivatives. For quantification purposes, if we assume that the zero-order spectrum obeys Beer's law, there is a similar linear relationship between concentration and amplitude for all others of derivative. Taken the difference between the highest maximum and the lowest minimum gives the best signal to noise ratio, but may lead to increased sensitive to interference from other components.
Okay, so then going to the results and discussion, here is going to be like the graphs that they did. So first, as my partners just mentioned, they used first derivative and the zero order, which is before the derivatization. So here A is before the derivatization. You see that the three curves are pretty much the same. If you want to know which each curve means, it's right underneath. Here you can see what each one um, means. And you can see that they are pretty similar, which is going to be a little bit difficult for us to read it, right? Because it will get with some interferences. But it changes a lot when you do the first derivative. So when you do this first derivative, you can see how the sensibility is going to increase, as she said previously. And so here is a dramatic difference, right? Here you see that curve number one, which is the complex between nickel and sorry, between copper and HBTU, has a very high maximum and a very low minimum, and around the same wavelength where it was the maximum absorption. Now it's a zero, as she mentioned it. Mathematically, it's just because we're in the peak, right in the center, there is no slope. Therefore, the derivative will be 0, right? So here we see the zero, the zero crossover point at 480. Here is also one thing that my partner was mentioning, which is the Beer-Lambert law. She said that we can assume that if the zero order or the original um, behavior will obey the law, then the first derivative will also do that. As you know, Beer-Lambert law is linear, and as you can see here is graphed. You can see it's not a perfect line. The r squared is not exactly 1, but it's pretty close. So we can say it is very good. You can see here that figure 4 is for copper, figure 5 is for nickel. Okay, so we can really not make any conclusions additional to the ones done in the paper originally. We considered them as counterproductive. They actually, I mean, all possible conclusions appear there. So we're just going to limit ourselves to mention them. And the paper says that, literally that the major contribution of this work was sensitivity range, as you saw in the graphs, the simple working conditions, because you saw that it was a neutral pH and room temperature that will be very good for costs and other variables that may be in the game, to say it for in one way or another. And so also the simple synthesis of HPTU. So HPTU, as I told you, is for doing a coordination compound. It is a ligand that it will make a coordination um, bond with the metals, right? And so this is a chelate, and it is also a chromophore. That's why they call them like that. Actually, in the paper, they mention how is the synthesis of the chromophore, because it's a little bit different as a conventional synthesis for the compound, but it's not actually directly related with the problem of determination of copper, so we did not went very deep into that. And well, these were the references. We used a graduate thesis done by a student here at the university. The second reference is the article, and the other two are some other documents that we used for this exposition. So thank you very much for your attention, and if you have any questions, you may ask.